Okay, software paradigms. I'm going to talk about 20 minutes or so. And in this talk, we're exploring general concepts in software development. And we're also exploring a range of the alternative disciplines within software, some of which we'll be touching on in the course and some of which we'll hardly be mentioning again. This particular talk is quite high level. There may not be a lot you'd follow up on subsequently. It's tended to give you a flavor of our view of the field, really, and organize some of our thoughts prior to plunging into more detail on the topics we proceed with. I'll start with a quote which embodies some of the principles around which we've organized this course here. And this is from quite some time ago, and it's an observation around how we can improve our programming capabilities. In particular, how can we learn good programming skills? And a lot of the learning comes from looking at existing programs. This is why in the course of our work here for the next 12 weeks, we'll be showing you a lot of code. We'll be exploring a lot of code in the labs, and we'll be reviewing code in the slides and in our talks. And we're hoping that through looking at code frequently and illustrating via code the principles we're uncovering, we can inculcate some key important practices and move your understanding of the discipline forward. Our talk this morning is in two kind of parts, really. I'm going to talk about software paradigms for a few moments. It's an interesting word to use, and it has some general context and meaning that is quite subtle, and I'd like to just spend a few moments talking about that. I'd also like to look at the stack I'm showing you here, which is I'm calling it a software engineering knowledge stack. It's quite ephemeral, really, but we'll walk up through this stack, exploring different concepts along the way, and perhaps we'll use that as a foundation to indicate what parts of that stack we're going to be investigating in our module. First of all, let me talk a little bit about software paradigms. Paradigm refers to a kind of a category or a set of entities that share common characteristics. More usefully, we might think of it as a conceptual way of thinking or describing something. It's a general, maybe class of concepts and values, given a name often, which we can recognize and use in conversation and in exploring the discipline further. The notion of a discipline being divided into paradigms is common across software and scientific disciplines. If we're looking at software, you may have heard of some of these terms in your careers to date: imperative programming, declarative programming, object-oriented programming. These could all be paradigms that have arisen in the history of computing. Some of these paradigms are alive and vibrant. Other paradigms are less visible these days and maybe heading towards more sunset type behavior. These paradigms, though, have a certain structure to them, and it's a structure that was uncovered not just in computing, but in science generally. And this is one of the most influential texts in the history of science and the philosophy of science. It's Thomas Kuhn's Structure of Scientific Revolutions, and it was published many years ago, late 50s, early 60s, I think. And he assessed that, particularly in physics, but also in science generally, paradigms arose periodically as the disciplines evolved. And those paradigms centered around communities, and those communities shared beliefs, values, sometimes a symbolic language, and also examples. And those communities became very active and very vibrant, and also they became very influential around various views of a given field. Now, why is that relevant to us? Well, he also coined the term paradigm shift, when one paradigm gives way to another. And it's quite common in science for these shifts to occur periodically. Periods of uncertainty and confusion can abound as a new paradigm takes hold. That new paradigm often represents breakthrough thinking, and often represents a community moving from one field to another new way of doing something. And we see this quite periodically in software. In fact, there is a proliferation of paradigms in software. And if we're looking at it from the perspective of programming languages, we find that a given language can support many paradigms. And in fact, these paradigms can in turn overlap and embody a set of concepts that are distributed in different disciplines. Trying to put sense in all this and trying to have an absolute taxonomy of the paradigms in force is impossible, really. But we do recognize that there are different schools of thought in software development. Those schools of thought are often overlapping and they're often in contention. And we're aware of those paradigms as we explore a discipline over time. For our module, these are the general areas, if we call them paradigms, that we're going to be exploring. Object-oriented programming, particularly principles within OO given the term solid, which are a venerable set of principles to guide the construction of object-oriented programming programs. Our core language is going to be Java, but we're also going to go beyond Java occasionally into successor languages, and that'll be the subject of one of our talks later on this morning, Kotlin being the language of choice. But in parallel with our exploration of OO programming, we're going to be talking about Agile methods as a whole, and particular two cornerstones of Agile thinking, test-driven development and automated configuration management, or continuous integration is also called. To illustrate these topics and these concepts and let's say paradigms, we'll be building little applications. The application is built in Java, and we'll be doing some network programming by ensuring we can have some interesting problems to solve that will ultimately be web applications or web services. I'd like to just take a walk through this knowledge stack I mentioned earlier, just again to set the scene for where we will be, and also to paint a picture of some of the key breakthroughs that have occurred in this field over the years. We'll go from bottom to top, and starting with programming languages. This is the bread and butter of many of your fields, particularly those of you who are programming very frequently. And you're probably adhering to a small number of languages that you've learned. Maybe you're focusing on one language in particular. When you're acquiring a programming language, you acquire an understanding of the syntax and semantics of the language, that is the structure and appearance, and also meaning. But over time, you're also accruing a set of idioms in the programming language. And these idioms are often ways in which you might apply the language in certain contexts. Very often these idioms are not known when the language is invented, and they arise over time and over experience with the language, or over experience with the language as it evolves. In fact, Java is one such language where many of the idioms in use came into use long after the language itself was first coined. Now, the evolution of language is quite fascinating, and Siobhan will be dealing with that in a talk in a few moments. Languages do have heritage, they do have predecessors, and they influence successors. And the range and diversity of languages is quite staggering. This is a drastic simplification here of some of the origins. And many of the languages, as we mentioned, embody paradigms: imperative languages, declarative languages, object-oriented languages. These all are clustered in different zones in this particular diagram here. And Siobhan will be exploring some of that with you a bit later on. Often when we're choosing languages, though, we're not going to the family tree. We're going to what is it we're building. Is it a web application? Are we building a game? Is it analysis? Are we building a mobile app? And languages cluster around these areas. Some general purpose languages can be suited to many of these fields. Others are quite specific and specialized, particularly in data analysis. As a programmer, we're usually keen on seeing, well, which one is popular, which one is rising, which one is falling, which one should I invest my time in, which one could have a positive impact on my career. You'll find a lot of tracking polls on languages, out there showing percentage change over year on year, which language is coming, which language is going. Surprisingly, though, if you look back 10 years, the top 10 is reasonably stable. It takes quite a bit of change for a language to break into that top 10 and remain there consistently. Some of these analysis center around Google search terms, and they try to give you a picture of which language is gaining in popularity and which is steady, which might be declining. CPHP here in decline, perhaps not too much of a surprise. Python, very dramatic growth here due to interest in analysis. Java, possibly in relative decline, although you will find other polls indicating that Java is reasonably stable. JavaScript there looking like it's steady, although you will find other polls and surveys indicating that its growth is explosive. Very unscientific field, really, trying to figure out which is the language of choice. But the top 10, certainly top 15, are well known. If I just go up this little stack just to make some observations along the way, once we've mastered a programming language, we're often, for studying programming, our next port of call is data structures and algorithms, or data structures and problems, as I've called it here. We would expect our language to support these now. We wouldn't necessarily be building these from scratch anymore, although there was a time when we did. And of course, we're also expecting our language to maybe have a toolkit of algorithms we can make use of. Common categories of algorithms that are the stock and trade of a programmer's world are searching, sorting, traversal, inserting, deleting into data structure, classification, merging, etc. These are the bread and butter, really, of the programmer. In our lab today, we're going to be doing some very small little Java fragments illustrating some of these concepts. For instance, on the right here, we have a data structure, a list, and you'll be using Eclipse to run this program, stop it, explore the program, look at the data structure in real time. In fact, our IDEs are powerful now. They can show multiple views of a data structure. A logical view, which might be the view we would draw on a whiteboard if we were contemplating a list, and also a physical view, which will show considerably more detail as to how the data structure is actually implemented by whatever library we're currently using. And you'll explore both of those today. Still on this knowledge stack, just going up one more level to design patterns. We consider these to be broader in scope than data structures and algorithms. They're working at a higher level of granularity. They're usually tied to a paradigm. So we talk about paradigms and patterns in an object-oriented context, or maybe functional patterns, which would be quite different. And these patterns aren't libraries. They're not code, really. They are solutions to known problems, particularly problems that are recurring in the field and problems that can be solved with the benefit of insights from previous solutions. It's a fertile area in its own right. Pattern thinking is largely driven by making the solution resilient to change. If the application we're building is a one-off and may never need to be modified subsequently, it's a prototype or disposable, then patterns are less interesting. But if the application is to survive, particularly survive changing requirements, changing platform, perhaps even changing programming language, then use of patterns could dramatically improve the lifespan and quality of the solution. And patterns themselves are further divided into levels in their own right. At the lower level, idioms. So programming idioms and patterns overlap to a certain extent. Indeed, patterns often gravitate towards idioms if they're widely used. We use the term design patterns for mid-level complexity, whereby we're dealing with classes and objects in general and their relationships. And patterns is often applied at a higher level to architectural considerations. Higher level patterns that embody broader approaches to entire systems. These are some examples of higher level patterns that you might encounter: domain, presentation patterns, messaging patterns, message router, pipes and filters, for instance. Here's an example of a pattern, and you'll notice I'm showing you code. It's kind of strange. And this actually is an extract from one of the programs in the lab today. If we're familiar with pattern thinking, we would be able to identify a pattern here fairly quickly. And the pattern would be the use of a static member of a class and also the use of a static function to access that member. That's the singleton pattern in action. And effectively, we are establishing what you might call the global one-off instance of an object in the Java context. Now, if you're new to Java, that won't make much sense yet. We'll be introducing Java in the next few weeks, and this code itself will be part of our introduction. If you're familiar with another programming language, you might see some echoes in the syntax we're using here, particularly if you're using C# or C++ or C. Some more design pattern examples. We do have another module on design patterns, which we may be offering next term. The patterns we visit in that module are the classic patterns still widely used today. These patterns are given names, and there is a canonical representation of these patterns in many programming languages, including most modern programming languages. So for instance, the pattern we just briefly looked at here is in the catalog as singleton. And you might have heard of other patterns over time. Perhaps you've come across the word command, or perhaps you've seen the word observer used in other contexts. They're the names of patterns with their own literature, their own examples, and their own trade-offs, which perhaps we'd explore in another context. Going up one level, components. Here we're talking about reusable code packaged for interoperability and published in known locations. Component thinking has been very central to the last 10 years of software engineering, particularly ways of making the components independent of acquisition and deployment. We essentially try to package reusable code, particularly reusable code that can be generalized to more than one application, into a component catalog, and hence into more widespread use. In your lab today, we'll download and use a component just for the fun of it. Here is another fragment from the program, one of the applications you will run in the lab. And here's an example here of a component which we would have downloaded. It's a component for turning a Java object into XML. And once we incorporate the component into our application, then we'll be able to reference it in our application and use it subsequently in the creation of objects and ultimately in the production of output, in this instance, an XML version of our data structure. So the IDE we're using understands components. The language we're using has a component packaging standard called jar files, and you'll get some experience of that today. More component definitions. I won't go to these in any detail. You can look them up if you like. Modern component research has moved on to services combined with components and combining very small or fine-grained components as microservices. It's a fertile area of research and also a quite rapidly changing area. Okay, I'll finish off shortly. Just keep on going up this stack. We're going to architectures. This is quite the highest level, maybe, possibly with the exception of frameworks, whereby we can contemplate an entire system or a system of systems. This could have been encountered during pattern thinking, but often we extract it from patterns and look at it more globally. And here we're looking at quite high level approaches to how an application is structured. For instance, a layered system with application, domain, and infrastructure services, or a pipe, ports, and adapter system, whereby the system is parceled into independent units communicating across known specific channels, or service-oriented architecture. You may have come across that, particularly those of you working in a service environment. Here we're not really talking about code. We may not even be talking about a paradigm. We're talking about high-level constraints on a system, and the focus very much is on the information architecture of the enterprise as opposed to a specific software engineering pattern or technique. This is beyond the scope of our course, this thinking. Lastly, I'll just talk about frameworks. We could have put frameworks below architectures. I'll put them above for the moment. And frameworks, in fact, are within the scope of our work here today because they're very influential in the styles of development that are most common in the industry, particularly web development and mobile app development. Both fields rely heavily on framework thinking. And without the presence and effective use of frameworks, it's difficult really to make too much progress. Frameworks in this context, we can consider them as large and sophisticated libraries designed to be extended and reused in a variety of contexts. They often embody a design that is complete and is designed to be then extended by the programmer to deliver a working application. We might think of it as a set of classes, perhaps, who already have an embodied relationship, and then our application becomes an extension of those classes, building on the relationships and abstractions in the framework itself, and taking the framework to its conclusion, which would be a working and running application. We'll encounter a framework when we move in to see if we can take our little laboratory experiments onto the web. And we've selected the Play framework as a reasonably easy to learn framework for building web applications. It's in Java and Scala, and we'll migrate some of our earlier labs into Play applications later on. Okay, what are we doing then in this course again? Having toured through this field, let's just summarize it. We're assuming you have a general programming ability. You have computer science in your background. Maybe you did an undergraduate degree in computer science and you had some programming there. Maybe you didn't do a lot since. If you didn't, you will still, I think, gain from this course because our first few weeks will be bringing you up to speed as soon as we can on modern Java and then pressing on with some experiments and exploration of the principles we're uncovering. Once we've Java out of the way, we're looking at solid principles, as Siobhan has mentioned. We'll be discussing those in more detail in a few weeks. Test-driven development is key to the entire course. Build processes, network programming via our Play framework, and we're also interested in moving beyond Java into successor languages and perhaps competitor languages, which are exhibiting a range of features which we think are important, and we will be touring them in some detail. Okay, that's my chat for the moment.